Hey, good morning, everyone. Thank you for joining today's compensatory class. And our class is now being recorded. In a minute, I'll be sharing my screen, and I think we should be ready to go. Okay, yeah, I think you should be able to see my screen now. Good to start. Okay, so last time we had completed the topic of routing and network layer control plane functions. And the only topic that remains in our first module on fundamentals of networking is the topic of transport layer functions. Primarily, we need to cover a few of the TCP and UDP concepts in order to be completely done with our basic fundamentals of networking that we will need for cloud data networking. So we should be hopefully be able to start and complete this topic on TCP UDP concepts today, so that tomorrow we can actually start with the next module, which is on enabling technology, the SDN and NFV. Okay, so very quickly, what is the transport layer? So recollect, we had said that in the TCP IP protocol stack, the layer immediately below the application layer is the transport layer. And the transport layer itself sits on top of the network layer, which is the IP layer. And this is what we were covering in the last class. So the function of the transport layer is actually to create a logical communication channel between the application processes running on two different endpoints. So in client-server communication, when the client sitting on one endpoint tries to communicate with the server sitting on a destination endpoint, then this communication path, which opens end-to-end between the client application process and the server application process, is a logical communication channel. And this logical communication channel, managing it and opening it and providing the required services to keep it functional, is the service of the transport layer. Okay, so this is what diagrammatically how I would show this logical end-to-end transport channel. It's a channel opened between the transport layer entity sitting on the two endpoints. On one side, you see a mobile phone, on the other side, a server in the enterprise network. And let's say I'm trying to access from my mobile phone some service in my enterprise networks. And this end-to-end transport communication channel is a logical channel that gets opened up between the two end machines. And on top of this end-to-end logical transport channel, the application layer messages will flow. Okay, so this is a logical channel that we are talking about opening. Now, in reality, what the transport protocols are doing when they receive the data from the application layer and transmit it over this logical end-to-end transport is at the sending side. Okay, Priyank's question, this will happen within a single AS as well, right? Or only across AS? Everywhere, irrespective of AS, Priyank. So the concept of AS doesn't make any difference to the transport layer function. Within and across autonomous system, it's the same thing. Okay. So this people who are familiar with network programming and have done any course on network programming or within a course on network, if you've written some network applications, created some network applications, will know the concept of socket connection. So you open a TCP socket or a UDP socket from the client side. The server side is already listening for messages coming on the TCP/UDP socket. So actually the term used in the network programming courses is the term socket interface. Okay? So the socket interfaces help us open up this logical end-to-end transport channel. So what the sender node is actually doing is receiving the application layer messages and breaking them down into smaller segments, depending upon the maximum packet size that can be transmitted over the intermediary network. So the larger application layer message, like a complete file, can be received. It can be broken down into smaller segments, and then this segment gets passed to the network layer. This is the bare minimum that the transport layer does at the sending side. On the receiving side, the bare minimum function that the transport layer protocol does is the reverse of it. It will receive segments of packets coming from the underlying network layer. It will reassemble these segments into a complete application layer message and then pass that application pass that back to the application. So if I have to say the minimum functions that any transport layer is supposed to do is one, this is what we call as segmentation and reassembly. Okay. Also short form written as SAR, SAR, segmentation and reassembly of application layer messages is the minimum functionality that the transport layer does. The second function that a transport layer does is actually multiplexing and demultiplexing application layers over the transport layer. So basically, in a way, we are saying when a logical end-to-end transport is opened up for one application, this end-to-end channel, any traffic flowing on top of it, identifies what application this message is meant for. In reality, in any two communicating nodes, right, or in any one node, there can be multiple applications on a particular endpoint. So if I draw a protocol stack, and I say application layer, there can be many applications sitting A1, A2, A3, sitting on top of a transport layer. Okay. So in reality, there can be multiple logical channels that may be opened by the transport layer towards different destination endpoints for different applications sitting on top. So when traffic is received on a particular logical end-to-end transport channel, the transport layer is actually making use of it to pass it to the right application. Similarly, when it gets traffic from one of the applications, it sends it on the right logical end-to-end transport channel to send it towards the right destination. So you can say that the transport layer is also multiplexing, demultiplexing traffic from multiple applications sitting in the application layer and sending their traffic towards multiple different destinations. Okay, so these are some of the minimal functions that the transport layer provides. When I say minimal, there are some more functions that are implemented in one of the transport layers. We'll talk about it in a while. So there are two most commonly used transport layer protocols that are used in the TCP/IP protocol stack or in the internet, to be in layman terms, and these are the TCP and the UDP transport layer protocol. So TCP is a short for transmission control protocol. It's a transport layer protocol which makes sure that the messages receive the application in a reliable fashion, which means if there are any packet losses that happen in the network, and we saw that there are various reasons why packet losses could happen. It could happen because of network congestion being the predominant reason why a packet loss can happen in the network, but also because of packet errors, which means certain bit errors might happen in the packet which cannot be corrected and therefore they may be dropped. So when packet losses happen in the network, but the application requires reliable delivery of all messages, then it is the responsibility of the transmission control protocol to make sure that every dropped packet is retransmitted. And in that way, TCP enables reliable delivery of packets. So we'll look at how TCP functions, but this is one of the key functions of the TCP transport protocol, reliable delivery of messages. It also provides in-order delivery. So if a higher layer application message is broken down into multiple segments, and these segments get transmitted into multiple different packets at the IP layer or the network layer, then we understood that each of them will be independently routed through the network. And because network conditions may change and routes may change on the fly, it's possible that later packets, some of the later packets may reach earlier and some of the earlier packets transmitted from the sending node may reach the receiver later. So in TCP, TCP plays the additional function of making sure that these packets are made back in order before they are delivered to the application. So reliable in-order delivery is one of the key functions that TCP implements. TCP also implements a function called congestion control, which basically is an attempt of the transport layer protocol to handle or address the congestion conditions in the network. How does TCP do that? We'll talk about it. A third function that TCP implements is the function of flow control. which is basically limiting how much traffic one sender is able to push into the access network and aligned with the service model or the service criteria or the service the subscription that the subscriber has. Right? That's one. Two, also making sure that the receiver is not getting overloaded with the traffic. So flow control is something that we will talk about in a while. Lastly, TCP implements a connection setup mechanism, which is what Jyoti has just mentioned as a three-way handshake method that that happens before any data transfer can happen. The connection is established between the sender and the receiver. It's a way that TCP uses to exchange key parameters between the sending side and the end destination side. We call it a logical connection setup. We'll see what it means to set up a TCP connection. But primarily it is because of this step of TCP, which is a connection, this step of connection setup, that we call TCP to be a connection oriented. Transport layer protocol. Okay. So connection oriented because one, it sets up a connection between the sender and the receiver. It's a logical connection, but it's explicitly set up via a three-way handshake of control plane messages. And that exchanges some key parameters or attributes between the sending and the receiving side, establishing the connection. The functions of flow control, congestion control, in order delivery of packets reliably over this connection further make TCP a connection oriented protocol because it is light, close to actually having a circuit switched communication method where a circuit is established and reliable in order delivery of traffic happens over the circuit. So while we are dealing with a packet switched network, TCP creates this logical connection and makes sure that packets are delivered reliably over this connection and in order delivery. And that is some of the reasons why we call it a connection oriented transport. UDP, on the other hand, is a more simple, we call it a no frills extension of the network layer protocol. So when we saw the network layer protocol, it was a best effort protocol. Best effort meaning if I'm able to route the traffic to the destination, then fair enough. If not, then that packet may get lost in the network. So it's a best effort delivery that the network layer does. Now UDP is also a no-frills extension of the best effort network layer or the IP layer. It doesn't provide any reliable delivery of packets. The delivery can be unordered. So if there are lost fragments of the application layer message, the responsibility is on the application to handle them. Unlike in the case of TCP, where TCP will address lost packets, if you're using UDP as the transport layer protocol, the application has the responsibility of handling lost packets. Now, when I say the application has to handle lost packets, it doesn't necessarily mean that the application has to retransmit the packet. There are applications where retransmission of lost packets makes no sense. Right? And these are often real-time applications. Right? So think of a WhatsApp call happening over an IP network. So the application is WhatsApp. The data corresponds to a WhatsApp call, which is a voice over IP call. The underlying network layer is a best effort IP net. Now, if I'm speaking, even the current class that we are having, okay, it's an example of a real-time communication. What I speak, that voice samples are getting packetized into IP packets and sent towards you. Now, if certain packets get lost, then there is no point in retransmitting them by the application layer, because in natural language communication, right, delayed reception of speech samples make no sense. So in a real-time communication, in some packets are lost, often applications will try to adjust them by various other means. So for a user, the effect of these lost packets will be intermittent interruption in that real-time communication. So if it's a voice call or a WhatsApp call, you'll have some intermittent disturbance in the communication. But because natural language is an interpreted language, and even in the loss of a few words, you can able to make out what is being said. A retransmission is not done. So in other words, I'm saying that it's not that UDP doesn't provide unreliable delivery, doesn't provide reliable delivery. It's often the need of the application that retransmission doesn't even make sense for lost packets. And therefore, the application prefers to use UDP, a no-frills, simple extension of the IP protocol, rather than going for a more complicated TCP protocol, which has its own overheads. Right? Overheads of connection setup, overheads of flow control, overheads due to reliable in-order delivery. So because the application doesn't require that, UDP is the preferred choice for such applications. Right? But even then, the bare minimum function that we talked of, which is of segmentation and reassembly of application layer messages, and multiplexing, demultiplexing multiple higher layer applications onto the transport layer is still a function that UDP provides, just that it doesn't have any of these other functions, these 4 additional functions that TCP provides. UDP doesn't have these functions. Okay, so that is why we call it a no-frills extension of the best effort IP protocol. Okay, now some services which neither TCP nor UDP guarantee, right, are delay guarantees or bandwidth guarantees. Right? Yes, Jyoti, as you rightly said, streaming live videos is also an example of UDP. Okay, but streaming recorded content, streaming applications like Netflix and all, I build them over TCP because of the buffering that I'm able to do. Okay? But if it's a real-time video communication, okay, then a real-time video communication is preferred to be over UDP because certain interruptions in video doesn't need to be retransmitted again. They're just lost and it's gone, it's past. Okay? There's no point delaying it and resending it. But buffering applications, like video on demand, they can still function over TCP because they require reliable delivery of all information. So yes, Jyoti, real-time streaming video applications, voice calls, video conferencing prefers to use UDP, whereas protocols which require reliability, like file transfer, downloading of video on content, and seeing that, which has its own buffering, prefer to use TCP. Okay, Teams will use UDP because Teams is more of a real-time communication. Whatever slide content. So somebody just said not seeing the slides. Yuvraj said it. I'm unable to see slides. Is anyone else facing similar issue? So had it been TCP, any lost packets that Yuvraj did not get would have gotten retransmitted, but that wouldn't have made sense because by that time I might have been on the following slide, next slide. Correct? So in real-time communication, it doesn't make sense to retransmit. Okay? So in such cases, video conferencing, voice calls over an IP network, UDP is the preferred protocol. It's a no-frills, simple protocol, only doing segmentation and reassembly of application layer. Okay, but important thing that I said on this slide is the last part. Whether it's TCP or UDP, neither transport layer protocol can provide any guarantees on the delay that an application layer packet will take through the network, nor can it guarantee any bandwidth that an application will be able to receive over the network. Does this make sense to everybody? Okay. Or does anybody feel that the transport layer should be able to guarantee any delays over the network or guarantee any bandwidth? I hope everybody understands based on our discussion so far, our understanding of how network layer behave. We know delay is a property of the network. We looked at the 4 components of a network. It depends upon the dynamic conditions in the network. So a transport layer protocol cannot guarantee an application any delay for its packets through the network. That's a property of the network itself. Similarly, the bandwidth depends upon, or the capacity, the throughput bits per second depends upon the paths that the packet is going to take through the network, the bandwidth of the interconnected links, and the other traffic which is sharing via statistical multiplexing the same links for their traffic. All of that will determine what is the throughput that a particular application will see over the transport layer. So, the services that a transport layer can never guarantee are delay and bandwidth. But the other things TCP can guarantee. Reliable in order delivery, it can guarantee. So we'll start with the simpler protocol, which is UDP, which, as we said, is a no frills, bare bones transport layer protocol for the internet. Because it's a no frills transport layer protocol, it's also a best effort service like IP is. So when UDP is being used for sending segments of application layer message, then some segments of the application layer message may be lost in the network. It's also possible that because different segments go via different packets, and these packets may take different route towards the destination, these segments may eventually be delivered to the application layer out of order. Okay? So all this is possible if you're using UDP. In which case, an application like MS Teams, which may be using UDP, has the responsibility of reordering packets at the application layer before making use of it. Okay, so all this responsibility falls onto the application layer because UDP would not do. And because of this reason, TCP, while it's called a connection-oriented protocol, UDP is called a connection-less protocol. Okay, so UDP is called a connection-less protocol because it doesn't ensure reliability of transmission. It doesn't ensure in-order delivery, which is characteristic of a connection, characteristic of a circuit. If I say I've set up a connection with the other party, whatever I say or speak or send will get transmitted through that connection, and that connection will ensure in-order reliable delivery. But because UDP doesn't do that, we also sometimes call it a connection-less protocol because there's no handshaking happening between the UDP sender and the receiver. No connection is explicitly getting established. And every UDP segment that is being sent by the transport layer protocol is handled independently of the other. They're not even bucketized into a single end-to-end logical connection. So it's a connection-less protocol. Okay. Okay, so I think this question I already answered. Why is there a UDP at all when there is no connection establishment? The reason why UDP is there is because it is simple. It's a no connection, no frills application, transport layer protocol. It can help application layers to blast away as much of traffic as they want, as they desire. Because there's no congestion control function also, unlike TCP. TCP will limit what you can send into the network. No frills means no additional functions. It's a general English phrase that we use to say no fancy things. Okay? Bare minimum, bare bones. So an application that uses UDP is not restricted in terms of the traffic that it can send to the transport layer. Unlike in TCP, where TCP will implement what we call as flow control or congestion control, all of which limits the amount of traffic that an application can send into the network. And the reason it does that is because TCP tries to manage the traffic sent by the application in a manner so that the traffic doesn't get lost. The packets don't get lost. If there's congestion in the network, it tries to implement congestion control methods to limit the traffic getting pushed into the network. If the receiver is not able to receive the traffic at a rate at which the sender is sending, it will eventually lead to packet losses at the receiver. To avoid that, TCP implements flow control. So TCP makes a lot of effort in making sure that packet losses are minimized. whereas UDP makes no such attempt. And therefore, UDP allows an application to just blast away traffic as much as it wants, as much as it desires, right? Even in the face of network congestion. Okay, so UDP is a very, very simple protocol, but often used for real-time application. Okay, okay, Ajit, your question I'm definitely not answering. Okay, if TCP is connection oriented, why can't it guarantee delay? Because it's connection oriented, but not the underlying network is not a circuit switch network. The underlying network is a packet switch network. I said it's a logical connection that gets established, but it's still over a packet switched connection. So I'll rather than answering that question, I'll say go back to previous classes and understand what is the difference between a packet switched and circuit switched network, and why can't a packet switched network guarantee delays? We've covered this adequately. Okay? But simple answer to your question is WhatsApp call is a circuit like it's like circuit switching. It's a connection oriented call between two parties, but it goes over a packet switched network IP. WhatsApp call doesn't give you a guarantee on delay. Right? Sometimes there's delay in voice communication over WhatsApp call. Okay, so a packet switched underlying network cannot provide any delay guarantees, and therefore TCP, which sits on top of a packet switch network, cannot do anything. It can't do magic to guarantee delay when the underlying network itself cannot. Okay? So TCP is connection oriented, but it is not circuit switching. It sets up a connection, but this is a logical connection. It's a socket connection that's getting established. Okay, thank you, Jyoti, in the meanwhile for answering questions around round trip time. We'll anyway come back to it. We'll come to it when we talk about TCP also. But thank you for handling that question right now. Okay, so this is what UDP is, a very simple protocol. Let's look at who uses UDP. We are just talking about this. A lot of real-time streaming multimedia applications will use UDP. Why? Because real-time video applications are loss tolerant. The video stopped for a while and then the video started again. It's fine. In a video call, I'm used to it. So loss tolerant. It's also rate sensitive many times, because if the traffic is coming at a lower rate, multimedia applications are built to handle that. If the throughput that can be achieved is less, I see a more blurry video. But if it's a high throughput connection that I have or throughput that I can achieve, then I see a more clear video. So multimedia applications are already designed or built to be loss tolerant and rate sensitive. And therefore, UDP is a better protocol to use for them. Okay. Okay. So Tushar's question about Tushar's question. Are there security concerns if no handshake between sender and receiver? No, the handshake doesn't guarantee any security, Tushar. Okay. The handshake happening between the sender and the receiver doesn't mean that the traffic is secured or that nobody can listen to it. And the handshake doesn't happen doesn't mean that the traffic goes to some unknown destination. Traffic forwarding is still happening based on destination address. Traffic routing is still happening based on destination address. So it is still reaching the same receiver. Okay. Connection oriented means certain different things, which once I go through TCP, you'll better understand. Okay. So security is not a part of TCP. Okay. DNS applications, which are more query response. I query the DNS server, giving it the fully qualified domain name, asking for the IP address. The response from the DNS server comes in over UDP. If I don't get the response, no hell is going to break loose. Why? Because I'll resend the request. I did not get a response to my query. Can you respond? And the next time the response can come back and I can function it. So applications like DNS, which do not rely on guaranteed responses, can function very much well over UDP. SNMP protocol works over UDP. A network manager, a network administrator sends a response to a network entity If an acknowledgement from the application comes in, I know the request has been successfully received. If it doesn't come in, I send the request again. That's how SNMP protocol works. So it can very well function over UDP. So a lot of applications which are loss tolerant but rate sensitive and in the sense that retransmission doesn't help them because they are real time in nature and they can actually adapt to the rate of traffic flow, like multimedia applications, video, primarily blurry video versus clear video. So such applications make use of UDP because it's a simple protocol. Okay, but if you are using UDP and still require reliability, then you have to build it at the application layer. Okay, if you need reliability, you should also look at implementing congestion control at the application. But in reality, if you need all of this, it's better to move towards TCP rather than using UDP. Okay, because TCP will already provide you reliable in-order delivery, congestion control, flow control, everything as part of the transport layer function. So there are a lot of applications which are better suited for UDP. Primarily the real-time, loss-tolerant, rate-sensitive applications. But applications like file transfer, which require in all pieces of the file to be successfully transmitted, they require reliable transmission, and therefore file transfer protocols run on top of TCP. Okay, so let's complete UDP before we move to TCP. So an example of an application that uses UDP is SNMP, Simple Network Management Protocol. So in SNMP, you have an SNMP client and you have an SNMP server. The application is the SNMP client on the left-hand side, and on the right-hand side, the application is the SNMP server. They sit on top of a transport layer called the UDP layer, which sends its traffic over the lower IP network layer, over data link layer and physical layer. So SNMP traffic gets routed through the network like any other IP traffic. So what is the UDP sender doing? The UDP sender passes an application layer message to the transport layer, UDP. Okay. UDP will actually segment this traffic into one or more UDP segments, add a header called the UDP header on top of it. This header has sufficient information which allows the recipient to know which is the application to which this message has to be sent. So the UDP header contains this information. Then once this UDP segment is created, it passes it to the IP. IP layer will create a packet out of it and route it through the network. So we've already talked about routing. What will happen? The packet will get routed up to the destination. Once the receiver receives this packet from the IP layer, right? So the UDP receiver receives the segment from the IP layer. It first checks the UDP checksum in the header. Checksum is a CRC. It's a field that is used to check if there are any bit errors that has happened in the packet header. Okay, it's error handling. So the receiver checks if any bits have gotten errored during transmission over the network. If bit errors have happened. If any bit errors have happened, then this UDP header cannot be treated as having the right values. It cannot be reliable. So then the packet has to be dropped. But if the UDP checksum passes, which means there are no bit errors, then it looks at the, it extracts the application layer message from the segment, looks at the UDP header, based on the UDP header field, determines what is the application to which this application layer message has to be delivered. That's the function of demultiplexing. So looking at the UDP header fields, demultiplexes and sends this message to the right application via the socket interface. Okay. So this is what a UDP layer does. So if you see, what we covered were the twin functions of segmentation and reassembly. If the application layer message was big enough, then segment it into multiple segments. But the other thing it did was multiplexing. Multiplexing it did when it added a UDP header here. it put in details for which application this message is meant for. And here it used that field to send it to the right application. So it demultiplexed. So this is what a simple protocol like UDP does. That's the function of the transport layer. Okay. Samantha has a question, sir. Applications like MS Teams will use TCP over SSL and streaming within apps uses UDP. So is this secure if even if UDP has no handshake? So Samantha, the simple answer is TCP or UDP have nothing to do with security. Okay. Neither TCP nor UDP ensure any secure transmission. Security is a different ball game. Okay. So nowhere in the functions of TCP did I mention secure transmission. Neither protocol provides delay guarantees, neither protocol provides bandwidth guarantees, neither protocol provides security for the application traffic. Okay. So security is not a function of the transport layers. And if it is, it's definitely not a function of TCP or UDP. So for security, you either use protocols like IPsec, which sit at the network layer, and IPsec has its own security protocols called authentication header or encryption security payload, ESP. These are two protocols which IPsec supports at the network layer for secure packet transmission. If you want security at higher layers, above the transport layer and below the application layer, you use protocols like SSL or TLS, transport layer security, which is a separate protocol than TCP or UDP. So neither TCP nor UDP provide security. Neither do they implement encryption, nor data integrity or hashing. It's not a function of the transport layer. It's definitely not a function of TCP or UDP. So don't get confused with a connection meaning security. Okay? Connection of TCP doesn't mean security. Connection oriented nature of TCP means reliable in order delivery. Reliable meaning no packet losses, or packet losses are handled, retransmissions happen. Doesn't mean security. Okay, so let's not be confused with that. Right, so let's look at what TCP provides to us. So TCP is considered, because it's a connection oriented protocol, it's considered to be a point-to-point protocol. One sender, one receiver. Okay. It's a reliable in order byte stream protocol. Byte stream meaning, unlike UDP, which deals with messages and message boundaries, TCP treats traffic coming from the application as if it was a stream of bytes, byte stream. Okay? So TCP sees it as a continuous flow of bytes of information coming from the application layer as a byte stream, which has to be sent over the network towards the destination. Okay? So we call TCP protocol as a reliable in order byte stream protocol, because what it is receiving from the application is not messages. There are no message boundaries in TCP. It's all bytes of information. So basically, TCP treats information at the byte level, and we call it a byte stream protocol. Okay, let me just read what Tushar has written on the chat. So it says Google has developed a quick protocol, which is quick UDP internet connections, a modern transport protocol that runs on top of UDP. And it combines the speed of UDP with reliability features of TCP, but in a more efficient way for services like Google Maps. So protocols can be modified the way we want as well, or is it the application layer modification? The quick, Tushar, is more like an application layer protocol. Okay. If you want to call it a transport layer protocol, it's definitely not a standard communication protocol. It can only be used in Google systems. Okay? So I cannot use quick to talk to a system, to let's say my laptop which doesn't support the quick protocol. Okay? So it has to be either in the application layer and then a part of the application, or if it is not a part of the application, then it has to be standardized. If it's not standardized, think of your laptop. If your Windows version that runs on your laptop doesn't support Quick, it supports the standard TCP and UDP. Then Google Maps cannot use Quick to run on your laptop. So it cannot be seen as a standard protocol at the transport layer. It's rather a proprietary extension built at the application. Okay. So when I said if you want to use UDP, not TCP, but want to have some functions, which is what I was writing, this slide said. Let me take you back a few slides. Yeah, this slide. If reliable transfer is needed over UDP, if quick transfer is needed, but you don't want to use TCP, then all of this has to be done at the application layer. And that's what quick is all about. Okay, so you built and you made certain changes to the application to find out a better and faster and more efficient way of achieving reliability in your communication while still using UDP as the transport layer protocol. So this is not a transport layer, it's an application layer modification. Answers your question, Tushar? Okay. So UDP and TCP are standardized protocols. When I say standardized, every laptop, every operating system, Windows, Apple OS, Android OS running in your mobile phone, iOS running in your iPhone, all of them in the transport layer will implement the same UDP and TCP protocol, which is a standardized protocol. Okay? It's a standard transport layer protocol, part of your TCP IP protocol stack. Okay, back to TCP. So TCP is considered a point-to-point protocol, one sender, one receiver. The sender is sending a byte stream towards the receiver. Okay? TCP has kind of created a logical connection. It's not a physical connection. There are no resources reserved in the network layer for carrying this traffic, and hence there are no delay guarantees. There are no bandwidth guarantees. It's not a physical connection. No resource reservation, no bandwidth reservation. Because underneath we have a packet switch network where there is no resource reservation happening. Right? So no bandwidth reservation. But what is TCP doing? It's opened up a logical communication channel between the sender and the receiver, and that's why it's a point-to-point channel that has been opened. A stream of bytes is being received. TCP manages the flow of this byte stream through the connections until it reaches the receiver. And it makes sure that these bytes of information are being received by the application in order. And not just that, in a reliable fashion. Reliable means no byte is lost in this transmission. So we know that underneath the network, which is transmitting this traffic, has no resource reservation. So packet losses may be happening. So there is definitely some magic that TCP is doing, because of which this byte stream which enters one side of the pipe is received on the other side and delivered to the application in order and reliably. What is it that TCP is doing? To be called a connection-oriented protocol, we'll just talk about that. Okay, this connection that it opens up, this pipe that I drew, it's a full duplex pipe, meaning data can flow both ways. It is not as if there is one sender and one receiver. Full duplex means that either of them can be a sender or a receiver. So when I send, the other party is the receiver. When the other party sends back some data, I become the receiver. So there is bidirectional data flow that is happening in the same TCP connection. And hence this TCP connection is called a full duplex data connection. Okay. So yeah, so Jyoti has already explained, in half duplex data flows only in one direction at a time. But in full duplex, the same connection can be used to simultaneously deliver data in both directions. Right? So if the parties connected via this connection are A and B, some data may be going from A to B over this connection. Some data at the same time may be coming from B to A. It's a full duplex connection that TCP has set up. Okay. Let me erase what I have already written. Okay, I'll come to cumulative acts later. That is TCP's way of ensuring reliable delivery. I'll come to it slightly later. Okay. TCP implements a function called the pipelining function, which is basically a combination of TCP congestion control and TCP flow control, which limits the overall traffic rate that an application can achieve. So in other words, you can say that throughput, but I should qualify it as application throughput. The throughput that an application observes in bits per second. The application throughput is limited or is controlled because of TCP congestion and flow control functions. We'll talk about these functions. It's connection oriented in nature. We've already talked about it, which means that before a sender and receiver or party A and B can start exchanging data, they first have to exchange certain control messages. This is called TCP handshake. This helps exchange certain critical parameters before data transmission starts. It helps initialize the state machine that exists at the sender side and the receiver side. And now, once the TCP handshake has happened, the sender and the receiver or party A and B are ready for data exchange. So it's called connection-oriented behavior of TCP. See? So yeah, its flow control sender will not overwhelm the receiver. So it's possible that when A and B are two parties talking to each other, A may be an Intel i7 processor, B may be a pretty old Pentium processor. Okay, so the two are not having the same computational speeds. So what if A sends traffic to B at a rate faster than what B can handle? B will get overwhelmed. It will not be able to handle this traffic. What will happen? Eventually, the packet will get lost at the receiver. Packet lost once again. So TCP also handles this as part of flow control. So let's look at each of these functions one by one. But before going into that, let's look at the packet format for TCP. Look at the header that TCP has, because some of this will be useful when we talk about these functions. So TCP header, the most important two fields that it has is the source port number and the destination port number. By the way, we did not see the UDP segment structure, but even UDP has the source port and the destination port number. What are these? These are the ones which are used for multiplexing, demultiplexing. So mux, demux function that we talked of, the port numbers are what are used for doing that. So the source port number identifies the source application. The destination port identifies the destination application. So when a segment of UDP traffic goes from sender to the receiver, the source port is identifying the sending side application. The destination port is identifying the destination side application. Okay? So well-known applications run on well-known port numbers. Does anybody know what is the port number on which FTP runs? What is the TCP port number on which FTP runs? What is the port number on which Telnet runs? Yeah, so Jyoti is answering it. 2021. What is it that Telnet runs on? 25. 23. Okay. Maybe I'm wrong. What is 25? I think one of the networking applications runs on 25 as well. SMTP. Okay. Thank you. So well-known network applications have already run on defined port numbers. The TCP segment, including as well as UDP segment, carries what we call as the destination and source port numbers, because these are used to multiplex, demultiplex the traffic towards the right application. Right? So both TCP and UDP have this, the port number. In addition, TCP has a sequence number. So as the name suggests, it is counting the bytes of data in the byte stream and putting that value over here. So let me give you an example. So let's say the byte stream of data is coming from the application. Okay. I pick the first byte coming from the application, I put it into this packet. So I make the sequence number 1. Let's say this carries 100 bytes. This segment carries 100 bytes. I've sequenced it, given it sequence number 1, because the first byte to 100 bytes, all of them are going in this packet, in this segment. Now, after this segment has been transmitted over the network, byte 101 has to be sent in the next segment. So the next segment will have a sequence number of 101. Okay? So you can say that the sequence number is the count of the first byte which is going in this UDP segment. Why is sequence number required? Because we know that these segments, when they are transmitted over the network, they might reach out of order at the receiving node. So TCP uses this sequence number to reorder the packets at the destination. Okay? So if I get a TCP segment which has a sequence number of 101, even before I receive the segment with sequence number 1, I will hold on to this and not deliver it to the application. I'll wait for the segment with sequence number 1 to come in first. I'll deliver that to the application and only after that deliver the next. Okay? And in reality, I'm not even giving messages to the application. What am I delivering to the application? A byte stream. So only when the segment with sequence number 1 comes in, will I deliver the byte streams 1 to 100 to the application first, and then I will deliver bytes 101 onwards to the application. So TCP makes use of the sequence number at the receiving end to deliver the bytes in order to the application. That's the use of the sequence number. This is something missing in the UDP packet. This is required for TCP in order delivery of bytes to the application. TCP also contains an acknowledgement number. Okay. Acknowledgement is the way that is used by a receiver to acknowledge to a sender that I have received bytes up to this count. Okay. So since we said it's a full duplex communication, every sender is also a receiver. Let's say this guy is node A. Every sender is also a receiver. Node B, when A is sender, node B is receiver. But when B is the sender, node A is a receiver. So A might have sent bytes 1 to 100 to B. So in this segment that A is sending to B, sequence number will be 1, indicating that the first byte is captured in this segment, and in reality there are 1 to 100 bytes going in the data part of this UDP segment. Now, if before the A sends 100 bytes, prior to that, B might have sent some bytes to A. It's a full duplex communication. So let's say bytes 50 to 200 might have come from B to A sometime in the past. So in the same packet where A is sending a sequence number of 1 to B, it's also sending an acknowledgement number 50 to B, indicating that the segment that you sent with sequence number 50, I'm acknowledging it. I've already received it. Okay. So in a sense, every segment of data that a receiver receives from a sender, it acknowledges it. So every data communication in either direction is acknowledged. Now, this acknowledgement might itself also be carrying certain data, as we see in this segment. It's also having a sequence number. It's carrying certain data, but it's also acknowledging what it has received in the past from the other party. Okay? So every reception is acknowledged by the other party with an acknowledgement number, and this acknowledgement number is the same as the received sequence number in the last segment. So this ensures what? Reliability. If I don't get an acknowledgement from a receiver, I have sent a packet as a sender, a segment as a sender, I don't receive an acknowledgement, I know that the packet is lost. I can take corrective actions. And what are the corrective actions that TCP takes? It retransmits the segment. Okay. So by using a combination of sequence number and acknowledgement number, TCP is able to handle in-order delivery because of the sequence number, and it is able to ensure reliable data transmission because if the acknowledgement is not received, the sender will retransmit the packet so that it will keep on doing this till an acknowledgement is received. So it will make sure that all bytes of information have reached the receiver. So it's reliable. Okay? So even though the underlying network is not providing reliability, packet loss can happen at the underlying layer. TCP provides the reliability by implementing retransmission and an acknowledgement method. Okay, this is the application data that is sent. This is the checksum. The checksum is also included in the UDP packet. I mentioned that on the earlier slide. The checksum makes sure that there are no bit errors in transmission. So it's like a CRC check. It's a some form of a more complex form of a parity checking, bit error checking. There are some other TCP options which we will right now not get into to keep it simple. There's a field in the TCP header which mentions the length of the TCP header, because there can be some TCP options which make the header variable length. So a length field in the TCP header mentions what is the length of the TCP header. There are 3 flags. Flags because they're 1 bit each. Reset, sync, and finish. These are used for the handshake. We will talk about that later. So these are used for initial 3-way handshake, connection management. Reset resets the TCP state machines. Sync is the first message which is used to synchronize TCP state machines. Fin is a termination of the connection, TCP connection. So these are 3 flags which are used for connection management. Start a connection, terminate a connection. The flags are used for those. RSF, 3-bit information. Okay. Very important field in the TCP header is the receive window size. This is a value that is sent by a receiver to a sender. And it indicates the number of bytes that the receiver is willing to accept from the sender in the next segment that the sender will send. It's used for TCP flow control. Right now, just remember that there's a field called receive window. When we talk about flow control, we'll see how it is used. Okay. There are a couple of other flags, C and E, used for congestion notification. These are used for congestion control. And there's an urgent data pointer, which is used for carrying some high priority traffic in a TCP segment. Once again, we'll ignore this for now, not get into those many details. Okay. So this segment structure, these fields we will come back to when we talk about flow control. We'll see how receive window is used. Okay. When we talk about congestion control, we'll see that these flags are used, congestion notification flag. And we've already seen that sequence number, acknowledgement number are used for reliable in-order delivery packets. These source port, destination port are used for multiplexing, demultiplexing, multiple higher layer application traffic. Checksum is used to make sure that there are no bit errors. So these are the important fields in a TCP header. Okay. By the way, that lab assignment I gave you for Wireshark, if you are seeing some TCP packets in that packet capture, you can actually blow open the TCP packets and see all these fields. You should be able to see that in that first lab activity. So Wireshark will be able to show you all these fields in a TCP packet that have been captured via the Wireshark tool. Okay, so lab assignment 1, you should be able to see all of this in all TCP packets. Similarly, if there are some UDP packets, you should be able to see those UDP packet header. Tushar, there is no date. I already said in the announcement, there's no submission for lab activities. Whenever you are conveniently placed, you can do it. But don't defer it to too late. because I'm sharing the lab activities aligned with the theoretical classes. So when the topic is covered in class, I give the lab activity for you to practice. So there's no submission date, but do it when you get time. Okay, so let's talk a little bit more about TCP sequence numbers and acknowledgements and how they enable in order reliable delivery, and what is the role of what we call in TCP as a sliding window. Yeah, Himo Bindu, it's not for test, it's only for practice. For your practice. Yes, Jyoti, I'll just come to the cumulative acting in a while. Okay. So I'll talk about what is cumulative act. Give me a moment, yeah, and come back. This is where we are going to talk about it. Okay. So how do we use the TCP sequence number and the TCP ACK field, which we just saw here, the two fields after source port and destination port? So we have source port, destination port, and then these two, sequence number, acknowledgement number. We said these are used for reliable in-order delivery. How? So TCP, we said, is receiving from the application layer. So this is application layer. This is TCP layer. What is the application layer giving to the TCP layer? A byte stream of bytes. So a stream of bytes is over the socket interface. See? So application opens a TCP socket. People again familiar with network programming know what I mean by a socket. It is the interface defined between the application layer and the TCP layer. Socket is the interface, API. Okay? Method that an application layer uses to talk to the TCP layer. So an application layer opens up a socket interface with the TCP layer. It's a form of API. Think of it like an API, an interface. Over that socket interface, it's sending a byte stream to TCP, sequence of bytes. What is TCP doing? It maintains what is called a sliding window. Okay? So it keeps on putting these bytes of information received from an application, let's say in a memory buffer. Okay? In a memory buffer, TCP keeps on collecting these bytes of information. Now, these bytes have to be transmitted over the network in a TCP segment so that it can reach the destination. So the ones that you see which are grayed out, these are the ones which have already been received or sent to the receiver and they have been acknowledged. So I'm grayed them out because I can now free up the memory buffer from these. They have already been received at the destination. So I sent them at some point in time, the receiver acknowledged them. So these are the gray bytes. They've already reached the receiver and already acknowledged. I can free up this memory buffer. This is done. The blue ones are the ones which have not. Okay, sorry. I made a mistake. Let me read my mistake. Forget what I said about the gray ones. Let me come. Oops. Yeah, forget what I said about the gray one. Actually, it's this way, left to right. Okay. So the green ones are those that I have sent towards the receiver and they have already been acknowledged by the receiver. Okay. So these green, I sent them at some point in time as data in a TCP segment. The receiver acknowledged them. I have received the acknowledgement at the sending node. This is the receiver. So these green ones are the ones I can free up from my memory buffer. I sent them, they've already been received, acknowledged. I can free them up from my memory buffer. The yellow ones are those which I sent next. I've sent the next yellow ones to the receiver, but the receiver hasn't yet sent me back an acknowledgement. I have not yet received the acknowledgement. So TCP calls them as bytes which are in flight. They are still on the way to the destination. They are in flight. They have not yet been acknowledged to be received. Okay. So TCP cannot free up these bytes. It will continue to store them in its memory buffer. Why? Because what if TCP never receives an acknowledgement? Because this data gets lost in the network because of packet loss. Then TCP must have a copy of these bytes in order to retransmit it again, to resend it, as Tushar said, right? So I need to keep storing it in my memory buffer in the TCP layer. Then there's these blue ones, which I've already received from the application layer, but I've not even sent them. They are also in my memory buffer. And I can send them, but I've yet not sent them. So there is no question of an acknowledgement being received for it. And then there are some other bytes of the application which have been received by the application, and I've buffered them in the buffer, but TCP treats them as not usable. I cannot send them. Now the question is, why can I not send them? The reason why TCP cannot treat them as unusable is because TCP maintains a running window of a variable size called n. This is called the window size n. This capital N of how many bytes can TCP send towards the receiver without getting an acknowledgement is a value that keeps on changing during the connection, but at that time instant, it's a fixed value. Okay. So this window size n is basically the maximum number of bytes that a TCP sender can send to a receiver waiting for an acknowledgement. So those are the maximum number of bytes that can in reality be in flight. After sending these n bytes, TCP sender has to wait. It has to wait for the acknowledgement to come. Only when the acknowledgement comes in will some of these yellow ones become what? They will become green. When they become green, I can slide my window n to the right. I can send some more bytes. So the blue ones may become yellow, and some of these gray might also become yellow. Okay. So what is n? What is the significance of this window size n? N is the maximum number of in-flight bytes that can exist, or in other words, it is the maximum number of bytes that a sender can send towards the receiver waiting for an acknowledgement. And then until it receives an acknowledgement, none of these gray bytes can be sent. They can remain in the buffer, but they cannot be sent. So they are not usable. How do I get the value of n? Or where do I get the value of n? N is determined based on two functions, the function of flow control and the function of congestion control. So this we are still going to talk about. Okay? As two of the other functions that TCP implements. Flow control, congestion control. So flow control and congestion control determine n. In other words, what is flow control? By determining n, what is flow control doing? It is limiting the amount of bytes that TCP sender can send towards the receiver. By fixing n, what is congestion control doing? It is limiting the number of bytes that a TCP sender can send into the network. Okay. So n can vary over a period of time for a TCP connection, depending upon TCP flow control and congestion control function. But at some instance of time, the value of n is fixed. This is the maximum bytes that the sender can send to the receiver waiting for an acknowledgement. Once the acknowledgement comes, these bytes can be freed up and I can shift my window of n to the right. And that is why this mechanism of keeping a window of n and shifting this window gradually as you keep getting acknowledgement for the previously sent bytes, it's called a shifting window method. Okay, so the bytes which are in the window, which fall within the window, they are the ones which are eligible for transmission towards the receiver. Okay, the yellow segment has already gone over the network. The blue one can be sent in another segment. The gray one cannot be sent until some of the yellow ones are acknowledged. So this mechanism, sorry, not shifting, sliding window. This is called TCP sliding window mechanism. Okay, it limits what the number of bytes that a sender can send to the receiver. So, okay. So you understand now what is the TCP sliding window. Right? So now if I have to send these blue bytes, yellow have already gone. What will be the sequence number? Sequence number will be the byte count of the first blue byte. Okay, so let's say this green byte was 1 and this last green byte was 100. Then the 101 was the first yellow byte and 150 was the last yellow byte. So the first blue byte is 1, byte number 151. We are counting bytes because it's a byte stream protocol. We are counting bytes of information. Yeah, Jyoti, correct. So sequence number will be 151 to send these blue bytes towards the review. Okay. Now, I may, as we said earlier, I may have received, okay, when the sender, when the receiver sends an acknowledgement, okay, I think on the previous slide I made a mistake. I'll correct it here. What is the acknowledgement number? It is not the same as the sequence number. Sorry about that. I said it on the previous slide. That was a mistake. So when the receiver acknowledges receipt of certain bytes, let's say these yellow ones have reached successfully the receiver. So bits 101 to 150, sorry, bytes 101 to 150 have reached the receiver. The receiver will acknowledge the receipt of these bytes by sending an acknowledgement and turning the acknowledgement flag on. Okay, when I turn the acknowledgement flag on, it means the TCP segment does not only contain data, but it also contains an acknowledgement, and the acknowledgement number is a valid value. Okay, so I turn the flag A on, I make it 1, A is equal to 1. So when the flag A is made 1, it means the acknowledgement number has a valid value, right? And this value is actually the receiver puts the value of the byte sequence, which is the next byte that it is expecting from the sender. So if the sender sent these yellow bytes to the receiver, these were bytes 101 to 150. The receiver received it. This is the receiver. The acknowledgement number that the receiver sends is 151. Okay, that's the acknowledgement number, not 101 as I said on the previous slide. That was a mistake. It's 151. So in other words, the receiver tells the sender, I have successfully received all bytes up to byte 150. Now I'm expecting from you byte 151. This method of acknowledgement is called cumulative ACK. Why? Because when I say 151 is the acknowledgement number, it's a way of saying that I have received everything from 1 to 150. I'm not just acknowledging these yellow bytes. I'm also acknowledging once again these green bytes. It's a cumulative ACK. So when I received these green ones, 1 to 100, receiver would have sent acknowledgement number 101, saying next one I expect from you is 101. I've received everything till 100. Then this guy sends the yellow ones, 101 to 150. He says acknowledgement number 151. In a way, he's saying I've received everything from 1 to 150. The next thing I'm expecting is 151. So it's called a cumulative act because it's acknowledging receipt of all cumulative bytes until byte 150. Okay, we'll see why cumulative act plays a big role. In the next slide, I'll show you different ways in which packet losses can happen in the network and how cumulative act comes in handy. Okay, we'll talk about it in a moment. Next slide. But before I go to that, the point of how the receiver handles out of order segment. Now, when you read the TCP standard, it doesn't say how you should receive out of order segments. It leaves it up to the implementation. Right? But in reality, we know that it's going to be a very simple implementation because the receiver can also maintain a similar receiver window. In that receiving window, whatever TCP segments are coming in, it is just putting them in the memory buffer. And it does not send it to the application until the bytes are already in order. So when the bytes are put in order, can it play it back to the application via the socket interval? So that's how it makes sure that the bytes are sent to the application in order. It makes use of the sequence number. No, Jyoti. So it's not bundling. Cumulative act doesn't mean I have to wait for all segments to be received, bundle them, and then send them. It's not bundling. I receive one segment, I send an acknowledgement. But I acknowledge all bytes that have been received till date, till now, in that connection. That's what it means by cumulative act. Gautam, that is a very open-ended comment. Please summarize again. I cannot. It took me 15 minutes on this slide. I cannot summarize everything again. If there's something you haven't followed, let me know. I can repeat a part of it. I can't summarize everything. Okay, so let me know what you did not follow in this whole slide. So we talked about sliding window. We talked about the importance of sliding window, the size of the sliding window being determined by the combination of flow control and congestion control functions. But given a size of the window, we know how the sliding window operates. Acknowledgement number, okay. So let's take this example again of the green and the blue. Green is byte 1 to 100. Yellow is byte 101 to 150. So when the green segment was sent from sender containing bytes 1 to 100, receiver upon receiving it sent acknowledgement number 101, indicating 101 is the next byte that I'm expecting from you. I've received everything until byte 100. Then the sender, when it sent yellow, it doesn't mean yellow has to be sent after, right? Let's say n. Let me make it a little more tricky. Let's say n is equal to 200. Okay. So can the sender immediately send 101 to 150? Immediately before even waiting for the acknowledgement 101? Question to the class. Can the sender receive 101 to 150 when n equal to 100? N equal to 200, even before receiving acknowledgement for the green ones? Yes or no? Yes, that's right, Yuvraj. See? What did we say about n? It is the maximum number of bytes I can send as a sender towards the receiver without waiting for an acknowledgement. So if n is 200, the first segment I send 100 bytes because maybe that's the maximum I could pack, or maybe that is the maximum I had received from the application by then. I put it into a segment, I sent it. Now, next 50 bytes came to me from the application. So even without waiting for acknowledgement 101, I can send the yellow bytes 101 to 150. Okay, let me make this n equal to 150 only. N equal to 150. So I've sent the yellow also because I could. My sliding window n equal to 150 allowed me to send those ones. But blue ones I could not. So the blue ones had to wait. So 101 to 150 have also gone. But I receive an acknowledgement afterward. This is on the time axis. We are going down in time. So I receive acknowledgement 101. What does this tell the sender? that until now, I only know that bytes 1 to 100 have been received. From my side, I've also sent 101 to 150. Let's wait. At some point later, this receiver will send acknowledgement number 151. When this is received by the sender, it knows that 101 to 150 have all been received. Okay. What could the sender have done at this point? At receiving acknowledgement 101, it would have shifted the original window, which would have been something like this, to where it is now. So it can, at this point, send the blue bytes. So the cumulative ACK is just acknowledging the bytes already received until now at the receiver. Right? What will have been received by the receiver, it's just acknowledging that. Okay. Sender makes use of it to shift its window. Whatever's been acknowledged, I can delete it from my memory buffer, shift my window to the right. Maybe send more. Like in this case, we could send, as soon as I got acknowledgement 101, I could send the blue bytes. Okay. So this is how sequence number, acknowledgement number work. Now, let's take a few examples to understand this better. Okay, let's take a simple telnet scenario. Host A telnets into host B. So in a telnet session, user types something on host A using the keyboard of host A, but that data goes to host B. It's meant for host B. That's what telnet is, right? So on host A, user types the alphabet C. So TCP sends a segment towards host B. What is the data that that segment contains? Character C. I've just taken some random numbers for the sequence and acknowledgement, indicating that C is byte number 42 that is being sent. And I'm maybe in the past, host B has already sent me 78 bytes. So I'm acknowledging and saying I've received 78 bytes from B to A at 79. So for now, let's assume 42 and 79 are some values. 42 indicating that there have already been from A to B, 41 bytes have already been sent. And from B to A, 78 bytes have already been received in the past. Now, when I type C, that will go in the data. It will be byte 42. So sequence number is 42. 41 were already sent. And I'm acknowledging, I'm saying ACK 79 means all 78 bytes that you sent me, B you sent me, I'm acknowledging them. Now, when B receives it, let's say the protocol is such that B has to echo back the data. I'm implementing the echo protocol over this telnet session. It's an application I've implemented over telnet. Let's call it the echo application. So whatever B receives, it sends back to A. So when B receives C, it echoes back C. So what again the data will be? Data will be once again C. What will be the sequence number? 79. It will match the acknowledgement. 78 bytes had already been gone and received by A. The next byte C is byte sequence 79. What will be the acknowledgement? 43, indicating that up to 42 have been received. The next acknowledgement is 43. Now, A doesn't have any more data to send. So what will it do? It just sends an acknowledgement alone, no data. Okay. So it will once again say sequence number 43, but acknowledgement 80. I'm acknowledging everything I've received till 79. Data C was received. So this is how ACK and sequence numbers work in TCP. Okay. Before I come to timeout setting, let me take a few examples of retransmission. First, to make this fully understood. Okay, so let's see how. Sorry, Gautam, what is the last packet sent? Did not understand that question. What did you mean by that? What are the ACK there? ACK is for the what I received from the sender. I'm acknowledging. It's a simple ACK. Okay, let's look at these diagrams. Maybe this will help you understand. It will firm up the understanding. So host A sends a byte, 8 bytes of data to host B. So it sends sequence number 72. Yeah, Priyank, let's look at these examples. This will help you understand. This it's the same sequence, not it'll help you understand. Let's look at these examples. It will help you understand how sequence number and acts are read. So in the first example that we have, host A has sent 8 bytes of data to host B. Sequence number was 92. What does this mean? This means that these are bytes 92 to 99. Correct? So host A is sending bytes 92 to 99 to host B. Sequence number will be 92. Data will consist of these 8 bytes of data, 92 to 99 bytes. Host B, what is the acknowledgement it will send? ACK equal to 100. Because it means I've received everything till 99 bytes. The next one I'm expecting from you is 100. Now, in this scenario, we are assuming the acknowledgement got lost. The data was successfully received by host B, but the acknowledgement got lost on the way back. Is there any way for host A to know that the data was received by B? No. Even if the acknowledgement is lost, for host A, it can never be sure. It assumes the data was lost. So it will wait for a timeout period for the ACK to come in. And if the ACK doesn't reach even in that timeout period, what will host A do? Retransmit. The same bytes 92 to 99 with the same sequence number 92. And this time hoping that the ACK 100 will come in. And when this ACK 100 comes in, what will happen to the sliding window? Shift right by how many byte positions? Shift right by how many bytes? 8, right, Jyoti? Right? So we shift right by Arup, sorry. So we shift right by 8 bytes. So this will happen to the sliding window, which means that if I have more bytes now received from the application, I can send them. Okay. So this is how TCP retransmission works. We'll come back to this timeout. How does this timeout get defined? How does TCP set a timeout? I'll take you back to those slides. But right now, assume there's a timeout waiting for that app. Okay, let's take another example. My sliding window was okay. No, my sliding window was of 30 bytes, let's say, n equal to 30 in this example. So the application first gave me 8 bytes, which was there on the previous example also. I sent them in one segment. That was this. Sequence 92, 8 bytes of data. In the meantime, I also got another 20 bytes from the application. So what does TCP do? It says n equal to 30. Yeah, I can send these 20 bytes as well. So what will it do? Sequence number will be 100. Another 20 bytes going. Okay, so these are bytes 100 to 119 going in this. Now, receiver, when it receives the first 8 bytes, what is the ACK it will send? ACK equal to 100. Because right now it hasn't even received 100 to 119. But as soon as it gets the next, it will send ACK equal to 120. This is the role of cumulative ACK, by the way, you asked Jyoti. So this is a cumulative ACK. It's acknowledging that I've received all bytes up to 120. Now, in this example, we are taking the example of premature timeout. So the ACK took longer to come in. The network delay had gone up. So the ACK took longer to come in. And what happened in the meanwhile? My timeout happened. So what do? I send, when I don't receive ACK equal to 100, I send sequence number 92 and 8 bytes of data again. I retransmit this, and this will get timed out somewhere here. But before that timeout happened, the second ACK comes in time. So I don't need to retransmit this byte. That is the benefit I get of cumulative ACK. So if this ACK was delayed or even lost, but this ACK comes in time, I don't have to retransmit this second batch of data again. Okay, this you will also see in the next slide, how cumulative ACK helps me. In this last example, ACK was delayed. In this example, ACK is lost. ACK is lost. ACK equal to 100 is lost. Packet loss happened in the reverse direction. ACK equal to 100 got lost. But ACK equal to 120 reached fine somewhere. So that covers up for the lost ACK as well, because it's a cumulative ACK. Right. So when the receiver sends an ACK, it acknowledges all bytes that have been received in order. Okay, Priyank says the screen is stuck. Is it for everybody, or are you able to see this slide where the ACK 100 is lost across against it? Only one diagram on the slide. Okay. Yeah. So Priyank, you're able to see. This is the one I'm on. Ajit is able to see. Okay. So in this example, ACK got lost, not delayed, but lost. Okay. And the cumulative ACK covered for it. So this is why TCP uses a scheme called cumulative acknowledgement, because it helps prevent unnecessary retransmissions of packets, especially when acknowledgements get lost on the way back or get delayed on the way back. Okay. So TCP in this example now can go ahead, as soon as it gets ACK 120, it can go ahead and send the next 15 bytes. Doesn't have to retransmit anything. Okay, so that is how TCP works. And now to the question on how do I set this timeout? So the timeout has to be at least larger than the round trip time. So I think Jyoti already explained what the round trip time is. Round trip time is A sends something to B, it takes some delay. Let's call it D1. B sends an acknowledgement back to A, it takes delay D2. D1 plus D2 is the round trip time, the time it takes for a packet to go from sender to receiver and for the acknowledgement to come back to the sender. That's the round trip time. So timeout that the TCP should use should be longer than the round trip time, because round trip time is what it will take for the packet to go and then the acknowledgement to come back. If I keep a timer which is too short, which means smaller than the round trip time, it will lead to premature timeout. The example we saw on the earlier slide. I'll unnecessarily timeout early and I'll unnecessarily retransmit some data. So I cannot have the timer too short. It cannot be less than round trip time. But if I make it too long, much longer than the round trip time, then I have slower reaction, because if a segment is lost, I'll keep on waiting for a very long time before retransmitting it. So my reaction speed is slow. And when my reaction speed is slow, my overall throughput that the application will be able to achieve will go down. I will take longer to transmit those very number of bytes of information from the application. So I cannot have a timeout which is too short, neither can I have a timeout which is too long. It has to be just slightly longer than the round trip time. But we've already learned that network conditions keep on continuously changing. And the delays in the network keep on changing. So the round trip time continuously will keep on varying, correct? So TCP implements a function to continuously estimate the round trip time. Okay. To do this, it implements a function called the exponential weighted moving average function. Okay. It's a simple statistical function where you exponentially decrease the influence of the past readings of the RTT measurement. So what is TCP doing? Every time I send a packet and I get an acknowledgement, what do I have? I get one reading of the round trip time. I send the next packet, I get an acknowledgement, I get a new reading for the round trip time. So TCP is constantly measuring round trip times, and this is what we call as a sample round trip time. Okay? I'm using the past samples to create a futuristic estimate. So it's like saying I'm looking at the history of my samples, sample RTT, and estimating the future RTT. And this is done by a function called EWMA, estimated weighted moving average. RTT can vary, Gautam says RTT can vary on the number of bytes transferred in every trip, right? No, not at all, Gautam. There is no role of the number of bytes. Okay, if you meant, yeah, Jyoti will just break immediately after I complete this. Okay, so maybe Gautam, you're right, because you're also including the fact that the transmission delay will vary based on the number of bytes. Yeah, in that sense, yes. But that's a very, very small impact to the overall RTT. Okay. So yes, Gautam, if your intent to saying was, and more the number of bytes, more the transmission delay at every node, and therefore more the round trip time, yes, you are right. You're right. But in reality, the impact of transmission delay to the round trip time is limited. And it is also fixed. We've talked about this in the when we talked about the delays, we said the transmission delay is more fixed. But yes, it depends on number of bytes in the segment, but the impact is limited. The bigger impact comes from queuing delay. So yeah, so to summarize, yes, what you said is right. But in ideal situations, the impact of the number of bytes is very minimal. Okay. Samanvita says, explain sample RTT. It's just a measurement of the round trip time. I send a packet, I get an acknowledgement, I measure the round trip time. I call it sample RTT. It's one sample value for the round trip time. Okay. So I have historical samples. I collected a sample at this time, then a sample at this time, 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 a sample at this time. I have multiple samples of round trip time. Can I use it to predict the estimated round trip time for the future? EWMA function, it's a mathematical function, it can do that. So we calculate the estimated RTT as the last calculated RTT with a weighing factor 1 minus alpha, and with a factor alpha, the current measurement. It's like saying all these were used in estimating the last RTT. I now give them a weight of 1 minus alpha, but the latest reading that I have, I give it a weightage of alpha, and I get the new estimated RTT. So I'm gradually diminishing the effect of the past readings. Okay, but still keeping them into use, because they already accounted for in this estimated RTT. So it's a mathematical function. If you don't understand it, it's okay. But this is what you will get. The reason why we use something like this is because samples can vary very dramatically. It doesn't reflect the real network condition. See, look at this. The light blue is your sample RTT. These are instantaneous measurements of the round trip. They can vary very dramatically time to time, but it's not a real view of the network. When I calculate using EWMA function and estimated RTT, I get a baseline which is closer and more doesn't fluctuate so much. So I use the estimated RTT and slightly more than the estimated RTT to set my timeout value. That's what TCP does. Okay, so this is all about how TCP implements sequencing and acknowledgement. The next thing we'll talk about, a couple of things remain, is flow control and congestion control. But as Jyoti said, let's take a short break. Okay, let's take a 5 minutes break. It's 12:40. Let's come back 12:45 and then go to the topic of flow control. The quiz will be most likely announced on Monday, Pradeep. Coming Monday, I'll announce it. Give you a week's time to take the quiz. Okay. So we'll take a break and come back by, okay, it's already 12:41, but let's take until 12:45 only. Let's take a 4-minute break. So 12:45 we'll start. Yes, Gautam, you get a week to complete the quiz, but once you start the quiz, it has a timeout of 15 minutes. Once you start it, you have to complete it in 15 minutes, but you can take it anytime during the entire week. So I'll announce it on Monday. Okay. Okay, can we start again? So the next topic that we want to discuss is the TCP flow control function. Now, okay, so when we look at the TCP IP protocol stack, we have the application layer, we have the transport layer where TCP sits, we have the IP layer, which is the network layer, and we have the lower layers, which is data link layer and the file layer. Do you have a background into which part of your laptop, let's say, each of these is implemented? You know that typically the data link layer is part of your network interface card. So if you have a network interface card in your laptop, an Ethernet network interface card, that's where the Ethernet data link layer is implemented. Correct? TCP and IP, they are both typically part of your operating system. and the application sits above the OS. So if you have a Windows machine, then TCP and IP are the implemented inside your Windows operating system. The application runs on top of the Windows OS. So how do these guys communicate? How does the data exchange happen between the network interface card, which implements the lower layer, the data link layer, and the operating system, which implements TCP UDP, and the application, which runs on top of the OS? How does data exchange happen? So this interface that the application has with the operating system, in reality, the TCP code is called a socket interface. This is people familiar with network programming would know this. It's called a socket interface. In reality, this is a memory buffer interface where the received bytes of information are put by the TCP code on the receiving side and pulled by the application from the, or read by the application from these receive buffers. So in other words, let me just use the animation over here itself too. So if any data is coming from the sender side, so some data is coming from the sender, it's coming over the network, what will happen? The network interface card will give it to the operating system. The OS IP code will pass it on to the TCP code. TCP will just put it into the socket buffer. And what you see going down this go arrow is actually the acknowledgement. TCP will immediately acknowledge the receipt of these bytes from the sender as soon as it has put them in the receiver buffer towards the application. Okay, the acknowledgement has already gone to the sender, what we just discussed on the previous slide, the ACK. Now, at some point in time, the application is supposed to read from this receive buffer and process this data. Right? So we say that the application is reading from the TCP socket. In reality, when it's reading from the TCP socket, it is removing this data from the memory buffers, receiver buffers, freeing them up. So that next set of data which comes from the network, from the sender side, the TCP code can place it in these free receive buffers. So these are two functions which are asynchronously happening inside a receiver. Data is coming from the network, TCP puts it in the socket buffer, sends back an acknowledgement. Process complete. Application gets scheduled, reads from the socket buffers, processes the data, frees up the receive buffer. That's a separate process happening. These are two asynchronous functions happening in the receiver protocol stack. Now let us assume that the receiver runs on a very slow machine. Yes, you are right, Gautam. So the socket interface is designed that way. Every application has its own socket interface, which means it has its own set of receive buffers. It's a one-on-one receive buffer. Every application has its own receive buffer with the TCP code. Okay, so that's the notion of a socket. So in network programming, when you say open a socket, open a TCP socket, you're actually initializing these receive buffers. They're dedicated for that application. Right. But the important thing I want to show you is that these two are happening independent of each other. TCP is filling these buffers. The application is reading and freeing up these buffers. Correct? But there are two asynchronous functions. What if the application is not able to read from these receive buffers at the same rate at which the data is coming from the sender and being filled in these receive buffers by the TCP code? What will happen? There are two functions which are happening. TCP is writing into these buffers all data that is coming from the network and acknowledging it. Application is reading from these buffers and then freeing up the buffer. But if the application processes data at a rate lower than the rate at which TCP is putting it, what Yuvraj said on the chat is what will happen. The receiver buffer will become full. And what will it manifest in? It will manifest in packet getting lost. Now this packet loss is not the same as packet loss happening in the network. in the network, packet loss happened because router queues became full. Correct? Here the packet loss has happened because the application is unable to process the traffic at the rate at which it is coming in. And that is why, as Jyoti said on the chat, that is why TCP flow control is there. So what is flow control? It is a method to reduce the incoming rate of traffic from the sender to align better with the rate at which the application can process it at the receiver. Okay. See these two diagrams, pictures on the left. This is the challenge which will happen when the network layer delivers data faster than the rate at which the application layer can remove it from the socket buffers. A little girl with her small mouth is trying to drink water. Same with the dog. But the water shower is throwing water at a rate much more than what she can consume or what the dog can consume. So what is happening? A lot of this water is just not getting consumed. It's getting lost. So to address this, what would you do to the water supply? Will you control it at the receiver or at the sender? At the sender. You will turn off the tap at the sending, reduce the flow of water so that the flow reduces and the girl or the dog is able to consume it. This is exactly what TCP flow control does. So I'm coming back to this receive window, which you saw in the TCP packet header, segment header. The receive window is, so when this acknowledgement goes back, the TCP code looks at how many bytes are free in this receiver buffer. And that value it puts in this receive window. So it makes sure that the sender does not send more bytes of data than what is available in the receiver buffer at the receiving end. And this is what, in simple terms, we call TCP flow control. Okay. Now, when the sender receives this receive window, what will it do? This will impact what? N, the sliding window size. Okay. Let's say my N was 100 at the sending side, but I get a value in the receive window which says 75. The receiver can only receive 75 bytes. Other 25, if you send, it will get lost. What will the sender do? It will change N equal to 100 to N equal to 75. Because if I send more than 75, the receiver is going to lose it anyway. There's no point. I'll have to retransmit it. So why send it at the first place? Why waste network resources? So the sender will reduce the sliding window size from 100 to 75. At some point in time, the application is able to process faster. So the receive buffer grows back to 150, let's say. The receive window that will be incoming will be 150. So I can grow back N. So that is why N is dynamic. It is dependent on flow control. A little while from now, we'll see N is also dependent on congestion control, but a little later. Right now, we are understanding how flow control impacts the sliding window size. And this is how a receiver controls the flow of data from a sender. So TCP flow control is end-to-end. We call it end-to-end because there's no role of the network here. It's the receiver which is controlling the rate of the sender directly. It's end-to-end. Okay. That's TCP flow control. Okay, so this is, I'm just skipping these slides. It's the same which I said on the other side. You look at the buffered data and you just put that in the window. In the thing. Okay, so before I get to congestion control, I'll now like to take up the connection part of TCP, the handshake, TCP connection management. Okay. So TCP connection management, as we said at introduction of TCP, we said even before data exchange can start between a sender and receiver, the sender and receiver exchange certain control messages. And these control messages are part of what we call as TCP handshake. Okay. In a way, It's a way to saying that the sender and the receiver agree to establish the connection. They are willing to establish that connection. And not only that, they agree on some initial parameters to be used to initialize their state machines. Example, what is the starting sequence number? So it doesn't necessarily have to start from 1. You can say, okay, we'll use a starting sequence number of 100. So what is the starting sequence number? But more importantly, parameters like the receiver window. What should be the value of sliding window n that I should initialize initially? What should be my first value of n? Sliding window. I don't know anything. So how do I initialize this n? So when we do this handshake before data transmission, each party exchanges its receiver window with each other. That's what I use to initialize n with, my sliding window with. This is why I need an initial handshake even before I start exchanging data. UDP doesn't require this because UDP has no flow control. UDP has no sliding window. You have data, UDP will bombard it over the network. Doesn't care whether the receiver is capable to receive it or not. It'll just blast it away. But TCP doesn't work that way. So it needs an initial handshake or connection management where you can exchange such parameters like receiver window with each other to initialize your values like n. Set your state machines in place. Okay, people who know network programming, you would have written codes like these. On the sender side, you would have said socket, client socket equal to new socket, host name, port number. So you initialize a socket. In reality, this is what triggers the TCP connection management. At the receiver side, the server accepts the socket. This demonstrates the willingness to establish the connection. So what is happening when you write a network code like this? So you open up a socket. When you open up a socket, TCP sends a SYN request to the receiver, sending the SYN flag to 1, SYN bit equal to 1. That was the flag we set, RSF, reset SYN and FIN. And it sets the initial sequence number. I'll start sending data with this initial sequence number. The server who's listening on the receiving port receives a SYN, it acknowledges it, and it says, okay, since you are sending, your first sequence was X, I'm acknowledging, I'm expecting X plus 1 going forward. So I've received your SYN, and I, on the other hand, will start from sequence number Y. This is my first sequence number. And the receiver will acknowledge the receipt of this sequence Y by saying ACK bit 1, I am expecting Y from 1 plus 1 from your side next. When this three-way message exchange happens, the state machine on the client side moves from listen to SYN send to established. The connection is established. Server is always listening on a port. For example, we said FTP was port 21. So it's always listening on port 21. As soon as it receives a SYN on port 21, it goes into a state called SYN receive. It sends back its own sequence number, gets an acknowledgement, enters into established. So both sides are now established, the connection is formed. This is the logical connection I was talking about. It's not the same as a circuit switch connection. There's no resource getting reserved. The underlying network is still a packet switch network with no guarantees for delay, bandwidth, nothing of that sort. It's just a logical connection between two parties who have exchanged a handshake to align on key parameters for the start of the data exchange. Once this is done, we can do the data exchange. So it's very close to how human protocols work. You've seen people do mountain climbing. There's always the mountain climber and then a person below the climber who's controlling the ropes. You know how the protocol they follow? The person who's going to take a step up further ahead will ask the person below if he's ready. So the person will ask on belay. and the one below will confirm saying, yes, belay on. But he doesn't know that the person climbing has heard this or not. So the person on top is supposed to say climbing. And this is a three-way handshake, which makes sure that both parties are aligned for the next step. In this case, climbing ahead. In the case of TCP, data transmission. Okay. So that's why we call TCP a connection-oriented protocol. I know time is out for our class, but I also know from last time that you guys don't have any other class today, correct? So I'll take 10 more minutes. It's a request. I want to complete TCP today, transport layer today. In fact, I want to complete this complete module on network fundamentals today. So we'll just continue another 10 minutes. Right, so last topic is congestion control. Now you all understand flow control. That diagram was very good, where the girl is trying to drink from a source of water, but the source of water is throwing water at such a high flow that the girl is unable to drink. So we had to control the source, not the network, the source. That was flow control. It was from the perspective of a receiver and a sender. But what is congestion? Congestion is not just about one sender and one receiver. It's too many senders sending data way too fast for the network to handle. It's not the receiver who's challenged. I may be implementing flow control. Maybe there are 1,000 people in the network setting up this TCP connection and talking to each other. Individually, all of these 1,000 pairs of sender receivers may be doing flow control. And every receiver may be fine with the rate at which the sender is sending data. But do you think the network will still be fine? Can the network still have congestion? Because 1,000 people are exchanging some data. If the network is not well designed, if the network capacity is limited, yes. Even if I have flow control implemented between the sender and receiver, the network may still be congested. Why? Because it's the case of too many people sending way too much data, way too fast for the network to handle. The network is not designed to handle that much traffic. Look at the road network. Eventually, your roads can only take as many cars at a time. In office hours, what happens? Too many people start moving to the office too fast. The road network cannot handle it. What do you have? Congestion. It's not as if the office doesn't have so many seats for the people who are starting from home. The office has enough seats for all people who are coming to office that day. So flow control is perfectly matched. But there are so many people going to so many offices that the road network is not able to take care of. So the network gets congested. How do you detect network conditions? How does it manifest? Or if I look at TCP, well, how would TCP know that there is network congestion? The manifestations are observed because of what happens in the network. When the network congestion happens, queues and routing buffers fill up. So the queuing delay goes high. And how does TCP get to know of it? Because it is measuring round trip time. I could have skipped that slide on round trip time. It wasn't necessary. But the reason I covered it very quickly, in fact, for all you care, that function EWMA you can completely forget. You don't need to remember it. How TCP measures round trip time. It's enough to know that TCP measures round trip time. And when it measures round trip time, it monitors that round trip time and it knows. So if I'm TCP and I'm monitoring round trip time, I'm seeing round trip time is going up like this. And this is the estimated round trip time, not the sample. Estimated RTT. It's going up. What is it an indicator of? Congestion in the network. If the round trip time, estimated round trip time is going down like this, what is it an indicator of? Congestion going low, reducing in the network. So the manifestation of a congestion in the network is longer round trip time. The manifestation is packet loss. I did not get an acknowledgement. I don't even know if the packet in the forward direction got lost or if the acknowledgement in the return direction got lost. But whatever happened, it's a consequence of network congestion. So TCP, based on its functions of round trip time measurement and tracking packets and packet losses and retransmissions, is very well in a position to detect network congestion. The question is, TCP can detect network congestion, but can it do something about it to help the network come out of that state? The answer is yes. So essentially, this is a problem which is different from flow control, is the important thing I wanted to highlight on this slide. Congestion control and flow control are two different problems. Okay? And even congestion control is one of the top 10 networking problems, just like routing was. Okay, so there are various approaches to solving congestion control. One method is what we call as network-driven congestion control method. Okay, I'm writing it down. Network-driven. What TCP does doesn't fall in this category. We'll talk about that in a moment, what TCP does. But one approach which many networks implement, packet switch networks implement, is called a network-driven approach towards congestion control. Okay. Okay. This is a different one. Yeah, this is network assisted. So let's talk about this first, and then I'll come to what TCP does. So network assisted, as the name suggests, as soon as a router gets congested, it sees its queue levels are filling up. The router provides a direct feedback to all sending nodes, saying, please reduce your traffic. I'm facing congestion. Okay. So routers can do two things. They can indicate the congestion level, level 1, level 2, level 3, level 4, make kind of a warning to the source nodes to reduce their transmission accordingly. Okay. No, Priyank, when I'm saying transmission, it's N. My application rate with this discussed now, it's completely dependent on the sliding window size. It is always much less than the overall transmission rate that you can achieve. That's the peak. The actual transmission rate, which we earlier talked about, that's the maximum you can achieve. You have a 100 Mbps connection at home, that's the max you can go to. But do you go to 100 Mbps? No, because TCP controls it. Okay, so one way is for network assisted congestion control, where the router gives you an explicit feedback. Your packet is going to pass through it. It sees your source IP and sends back a notification to the source IP saying, reduce your rate. I'm facing congestion. My congestion level is currently level 4. Or it may even explicitly send back a sending rate saying, don't send more than so many packets per second. What does this help? This helps the sender to control its value of N, or it helps control the flow of traffic out from the sender. So this is called network assisted congestion. There are a lot of algorithms that are implemented that routers support. There are techniques like ECN, explicit congestion notification bit. That is part of the ECMP protocol, which routers use to send a direct feedback back to source nodes telling them, I'm congested, reduce your flow. So these are called network assisted congestion control. However, right now we are not too interested in them. I just wanted to introduce this, that there are ways in which the network can indicate congestion to nodes and they can reduce it. But TCP congestion control is actually more of an end-to-end congestion control. We saw that TCP is an end-to-end protocol. It doesn't exist in the network. TCP sits on the source and it sits on the destination. It's an end-to-end protocol. So what TCP uses is, it doesn't wait for any explicit feedback from the network. It infers congestion from the observed packet losses, loss of acknowledgements, and from the increase in round trip time. This is what TCP uses as an approach to detect congestion. And without even waiting for any explicit feedback from network based on these network assisted congestion techniques, what does TCP do? It immediately cuts down its value of N so that it reduces the rate, sending rate, until congestion can come. So this is called TCP's AIMD behavior, additive increase, multiplicative decrease. It's characterized by its sawtooth behavior, like a sawtooth. Right? You use carpenters use that for wood cutting, the saw. So it looks like the tooth of the saw. It's called a sawtooth approach. So on the y-axis is the rate at which the TCP sender is sending. This is completely driven by your n, the sliding window. And this is time. So what this sawtooth behavior is showing you is that TCP alters the sending rate, in effect the value of n, dynamically, so that based on the congestion in the network, it can reduce the traffic that it sends in the network. Okay. How does it do that? AIMD stands for additive increase, multiplicative decrease. What it does is, as soon as, okay, additive, let me first bring up both and then I'll talk. As soon as TCP detects a packet loss, it cuts the sending rate by half. So if n was, let's say, 100, it makes it 50. It cuts the sending rate in half as soon as there's a loss. Why? Why half? What? This is why we call it multiplicative decrease. We've suddenly decreased it by a factor of half. I immediately cut it because once the network is congested, I've detected it via loss event. Packet loss happens when? In the extreme condition, network is already congested. So there's no point sending any more traffic in the network. They'll all get lost as well. Rather, if I cut the traffic dramatically, I'll help the network come out of congestion very quickly. So this is what TCP follows, multiplicative decrease, cut it by half. But then after cutting it by half, how does it grow the rate? Every successful packet that goes through, I send a packet, I get an acknowledgement. This is a successful scenario. I can't remain at half. So it also implements what is called additive increase. Every time I'm able to successfully get through a packet, I increase the sending rate by 1. So this is the behavior you'll see, additive increase. This slope is additive increase, gradually increasing the speed. But if the congestion hits, which it hits here, dramatic decrease. Then gradual increase, then dramatic decrease, gradual increase. This is how TCP behaves. Yes, Tushar, this could be one of the reasons why you see higher download speeds earlier, but then gradually you'll see the speeds going down. As the networks get congested, TCP adjusts the value of n. So when Priyank said transmission rate, that's the maximum 100 Mbps. But TCP will limit it to 10 Mbps, 80 Mbps, to whatever it is based on the network condition. Okay? So in a sense, I'll just summarize by saying that the sliding window n plays a very big role in implementing reliable delivery. Itself, it is controlled via two functions, flow control and congestion control. And this is what TCP is all about. Okay? UDP has none of this. So UDP will never care even if the network is congested. If, in fact, if you are a malicious user whose intent is to bring down the network, you will use UDP, not TCP. You'll just use UDP to launch a distributed denial of service attack on the network, bombard the network with traffic. Okay? And that is where other techniques for flow control come in. That is where the role of the internet service provider comes in. There are link layer functions implemented for flow control called you may have come across this leaky bucket algorithm. That is implemented more at the link layer. Okay, so there are, for those kind of situations, there are link layer protocols like leaky bucket, token buffer, which take care of such kind of malicious users. And this is done by your internet service provider. He will control the rate at which your traffic enters into his network. Okay. So this is all I wanted to cover, guys. Thank you so much for staying another 15 minutes and for agreeing for this compensatory class. We are done with the network fundamentals part of our course. At start of the class, I said we'll take 5 classes to do it. We eventually ended up taking 6. Most likely we'll cover up. If not, we'll sometime take another extra class to do it. But I'm hopeful we'll cover up at some point in time. But we are done with network fundamentals. The next module that we have to start tomorrow is the enabling technologies for data center networking. So we will talk about SDN tomorrow for sure, and if possible, also cover NFV. Yes, midterm up to SD and NFV, everything is going to be there. So tomorrow's class we will still have will be part of midterm, and if we can't cover SD and NFV tomorrow, then even the following class. I'll let you know till when we have the syllabus. I'll let you know. There's still 2 classes to go. Okay, I'll let you know what is the syllabus. But my plan is definitely till NFV, SDN and NFV. So 2 modules: network fundamentals and enabling technologies for data center networks. Okay, thank you everyone for joining, and see you tomorrow again at 10:30. Have a good rest of today. Bye-bye. Okay, Varan Prasad's question, upload slides in advance. I answered to somebody in the past, it's not possible because I don't know how much I'll be able to cover. And I also change slides before the class. I modify them. So I'll try, but I can't commit on that. Jyoti's question, will we get algorithms in midterm? It's more of conceptual questions that you'll get. I'll not ask you to tell me how EWMA is implemented or things like that, but more conceptual questions. Look at the last semester question paper, you'll get an idea of what kind of questions come in. Okay.